All right, let's jump right in. We're not just talking about RAG today. We are going to architect its very foundation. I'm going to walk you through the complete blueprint for a real production-grade data ingestion pipeline. You know, the kind that stops your RAG system from failing before it even gets off the ground.
So here's our game plan. First, we'll nail down the core problem every single architect runs into. Then, we'll build our pipeline stage by stage. We'll start with a fast sweep for some quick wins, then move to a duplication funnel to just crush all that redundancy, and we'll finish up with a quality gate as our final line of defense. And at the end, we'll zoom out and see the whole blueprint in action.
So let's kick things off with the architect's biggest headache: digital trash. This stuff is the silent killer of RAG performance. It's the real reason why even the most powerful, well-tuned systems just fail.
I mean, think about it. Why is your RAG system hallucinating or giving you the same answer 3 different ways? It's the question every AI team is asking, but the answer isn't buried in your model parameters or your fancy prompt templates. Nope, the root cause is almost always hiding in plain sight.
The issue, it isn't your model. It's your data ingestion pipeline. It's the classic garbage in, garbage out problem, just, scaled up to a terrifying level. The problem is purely architectural. We are feeding our vector database what I like to call digital trash. And today, we're going to build the automated system to stop it.
Okay, so this brings us to stage 1 of our pipeline, our DAG, or Directed Acyclic Graph. We call this the fast sweep. And the principle here is really simple. You start with a cheap, fast, and deterministic cleaning. These are your easy, quick wins.
And it all starts with something super simple: canonical text normalization. This is just a quick, deterministic pass to make sure that text like AI agents work, with a capital and an exclamation point, and AI agents work are treated as exactly the same thing. Getting this right makes every single downstream step so much more effective.
Next up, we do a structural cleanup. This means automatically stripping out all that recurring boilerplate that just pollutes your chunks and completely skews your similarity search. We're talking about headers, footers, cookie banners, all those legal disclaimers, all the junk that adds tons of noise but zero signal. Seriously, think about your own pipeline right now. How much of this stuff is getting embedded?
Now, here is an absolutely critical design principle. This stage and every single one that follows has to be idempotent. What does that mean? It means rerunning the pipeline on the same data won't create duplicates or change the outcome. This is what makes your system robust and predictable, and it's totally non-negotiable for any production environment. All right, now for the heavy lifting. Stage 2, the duplication funnel. This isn't just a single check. It's a multi-tier strategy, and it's designed to get rid of redundancy in the most cost-effective way possible.
We really have to approach this like a funnel, right? We move from the fastest and cheapest checks to the most computationally expensive ones. We kick it off with the fast tier, exact hashing. Then, we move on to the medium tier for near-duplicate detection. And only for what's left over do we proceed to the deep tier using those expensive embeddings for semantic similarity.
This table right here, it maps each technique to its cost and its purpose. Exact hashing, fastest and cheapest. It's ideal for identical files. Near-duplicate detection, using algorithms like min-hash, is perfect for those structural clones, like version 1 versus version 2 of a policy document. And finally, you've got semantic search with embeddings. Yep, it's slow and it's costly, but it is the only way to find documents with different wording but the exact same meaning. This is our core strategy.
This hierarchy, hash, then simhash, then embeddings, this is probably the most important takeaway here. By filtering out the easy duplicates first, we dramatically reduce the amount of data that ever has to see that slow, expensive embedding model. This is not just a suggestion. It's a fundamental rule for cost optimization in any large-scale AI pipeline.
So how do we stick to our idempotent principle here? It's actually simple, but it's super powerful. We store the hashes from our checks in a key value store. Before we process any document, we just check if its hash already exists. If it does, we skip it. That's it. That is our idempotent ingestion gate, and it prevents reprocessing and all those messy duplicate entries.
And that brings us to the final stage before any of our content even touches the vector store. Stage 3, the quality gate. Think of this as our last line of defense, our final guardrail against low-quality data getting through.
So here, we do something pretty clever. We use a small, fast, large language model, think like a 7 billion parameter model. Not as a generator, but as a judge.
Its only job is to score each chunk for information density and relevance before we spend a single cent on embedding it.
And we give our little LLM judge a very simple rubric to follow. A score of 1, that's for junk. Incomplete sentences, broken text from an OCR, random code snippets. A score of 5 is for, low information boilerplate. And the score of 10, that's reserved for the good stuff. High density, valuable information. This is our automated quality signal. And here is the architect's rule, and it's a simple one. If a chunk scores below a 5, it does not hit the vector store, period. The implementation is ruthless, I'll admit, but it is incredibly effective. Low-quality content gets dropped, and it never ever incurs an embedding or a storage cost.
So, we've seen all the individual stages, right? Now let's zoom out and look at the final blueprint. This is where we see the complete production-ready architecture all working together in harmony. And here it is, the complete system. This is our idempotent ingestion DAG. Just follow the flow from left to right. Raw, messy documents come in. They pass through our first 2 stages. That's normalization and structural cleanup. Then they hit that multi-tier deduplication funnel we designed, checking all the hashes and signatures. And finally, they face the LLM quality gate before anything is allowed into that clean, pristine vector database on the right. Every stage just builds perfectly on the last one.
So what's the big payoff for all this architectural work? Well, it's not just higher quality answers. It is a massive, tangible reduction in your operational costs. We're talking a 30 to 70% cut in your embedding and storage expenses. See? Clean data is cheap data. Look, if there's one thing you take away from all this, let it be this. Building a robust, automated, and idempotent ingestion pipeline is the single highest leverage thing you can do to improve your RAG system's performance. It delivers so much more value than just endlessly tweaking models or prompts.
Which really just leaves us with this one final thought. It's a mindset shift that separates the experimental projects from the real production-grade AI systems. Stop tuning your retriever. Start architecting your data pipeline. The foundation is absolutely everything. So what's the first stage you're going to build?